Hi, everyone online. Could somebody give me a thumbs up as to whether or not you are hearing me? Fantastic. Thanks so much. And I'll start the slides in a second here. Okay. Terrific. Good morning. So we're going to continue basically where we left off yesterday. We're going to start with image quality, and then we'll get into X-ray imaging and sort of X-ray production, how X-rays get absorbed by the body, and how you formulate an image with that process. Before we get there, are there any quick questions, organizational questions about the course that I can clear up right away? Okay, and same as Monday, I'll stick around after the lecture to answer any questions about the material or the course, okay, for the office hours. You can, if you want, look at the lectures. These lectures have not changed in a couple of years, and so, because of COVID, we taped them all. Everything's on, online, so you can watch something that's going to be very similar to the lecture I'm just going to give right now. And the advantage of doing it at home is you can watch it in like 1.5x or 1.75x, as you know. I mean, you've all experienced this now. And I always find it amazing that, so I watch some of these, I review what are in these lectures, and I watch them at 1.75, and then you go back to normal and you sound absolutely drunk, right? I mean, it's just, whoa, do we really speak that slowly? So you get an idea of just how slow the information transfer is by flapping meat in your mouth and vibrating, air. It's just really, really slow. It's like 10 baud or something like that. That's the information rate. It's terrible. But anyway, okay, so we're going to continue with image quality, then get to X-ray imaging. Okay, again, just to review those concepts that are exceptionally important. These are all talked about in Prints and Links, if you want to read the chapters on that. Let's start with what is contrast and what is an image and signal modulation in space. So if I have a signal here, which is just, let's call this A, we're going to have an image fxy here, and with a signal A. And if A is everywhere, then that is a very simple image, right? That's the null image. There's nothing there. It's nice and uniform. If we start modulating the signal as a function of position in space, we start getting an image, okay? That's all an image is. It's just modulated signal as a function of position in space. And so here we've modulated that signal with a sine wave of a particular relative amplitude to A, right? And the equation is down here. Here's the sine wave. We just change B, right? And we create a deeper sine wave and an even deeper sine wave. Okay, so there's 4 very simple images, right? And the reason we're introducing this concept is because these sine waves that are in a particular direction with a particular amplitude are the basis functions from which we can construct virtually any image. We just have to have enough of these sine waves in enough different directions, right, to reconstruct a picture. And that's called the Fourier decomposition of that 2D function, right? And a lot of what we'll talk about is how do sort of sine waves like this get modulated as they pass through our imaging system, right? So if I have in one dimension a sine wave that's the input, right? So this is space in this direction, this is brightness, and this is the true input. This is what exists in the world. I image it with my camera or my medical imaging system and ask, what's the relative amplitude of that sine wave when it comes out the back of my detector and image reconstruction? And the modulation of this frequency, if this is a sine wave, the modulation at this frequency gets a particular value, right? B, and that you can characterize the entire system and how it images a particular object with different spatial frequencies in it by looking at how each spatial frequency is modulated. Does it decrease the power of that spatial frequency as it goes through? Does it relatively increase the power of that spatial frequency as it goes through? And so this concept of basically the change in the amplitude of sine waves as they pass through your imaging system is an important one. You can imagine if you take a camera, say you have a Nikon camera and a Canon camera, and you want to know which one of these is better. I want to know which one gives me the highest resolution. So what we can do is we can put a test pattern on the wall, and that test pattern can just consist of stripes up and down, and those stripes get closer and closer and closer together, and you just keep taking pictures with the two cameras, and you find out which camera is the first to change that stripe pattern into just a mean value. When do the stripes go away? And it has higher resolution than the other camera. It's a pretty simple concept. So here's an example of three spatial frequencies that we're going to look at and see how they get transferred through our system. So the signal in space, the real signal that's input into the camera or the system, these are the stripes on the wall. Here we have 1 cycle per millimeter, 2 cycles per millimeter, and then 4 cycles per millimeter. So the stripes get closer together. Okay. And when we take the picture and we look at our result, we find that at 1 cycle per millimeter, this is this is actually a bad illustration in some ways because this is not a sine wave. You can see this is a rectangle function. But anyway, we have a very dark, very bright, very dark, very bright. What comes out of the imaging system is something that looks like this, right? So it is blurred, but the depth of the dark stuff down here and the height of the brightness up here has not changed that much from the God-given truth. At a higher frequency, I get a picture like this, and then eventually at a high enough frequency in cycles per millimeter, there's a lot of attenuation that occurs and you get a picture that looks like this, right? And so now those stripes are actually blurring together such that the amplitude of the stripes is diminished extensively as we go from lower to higher frequencies. And eventually it's just an average value of what's on that screen. You can plot the amplitude of that relative diminution or decrease in amplitude of those sine waves as the frequency of the sine wave increases. So here's 1, which corresponds to this. 2 cycles per millimeter corresponds to this. 4 cycles per millimeter to this. And here's how much it gets attenuated by our system. If we do this for every frequency and fill out this continuous curve, right? That is called the modulation transfer function for our imaging system. And that pretty well completely specifies the spatial resolution of the system, okay, the shape of that modulation transfer function. Most of them, when you characterize the system, look like this. They look kind of like a blob, right? So they pass things that are very a constant signal through just fine. And then as you get to higher frequencies, it gets diminished, the power gets diminished. And so the width of this blob is also a characteristic number for the system if you can characterize this function as a simple Gaussian, say. So you have a formula for that function, you fit it, and then you have a parameter that gives you the width of this Gaussian. Now, we looked at this last time in terms of the point spread function, but remember that thing was in space, right? So the units I was measuring, this half height, were in millimeters for the point spread function. This is different. We're measuring this in terms of cycles per millimeter, right? So it's a frequency. It's like how many oscillations per millimeter do I have? Okay. So they're very complementary functions. They specify kind of the same thing. One is the point spread function showing you how a infinitesimal dot shows up with your image. This one shows how sine waves are diminished as you get to higher and higher frequencies. It turns out that the Fourier transform of this thing is the point spread function. Inverse Fourier transform of the point spread function is this thing, right? So they're just Fourier pairs. Right? So as this function gets wider, i.e. you have more power at higher frequencies, so the thing gets wider, the point spread function gets narrower, right? So the dots get smaller. The dot that you can resolve gets smaller, okay? And then
Professor,
oh yes.
a couple of slides back, why did the AC component have a magnitude of the H rather than the H itself? Like, can you go back like 2 slides back where you showed? Yeah, in this one, why is there a magnitude for the H of U0?
Of H?
Yeah.
Oh, it's just we don't really want to talk about any kind of phase shift that the this system could also modify the signal by also shifting its phase. So we're just looking at just the absolute magnitude of the diminishing signal, right? So it just simplifies it.
Okay, thank you.
Right. Is that okay? Okay, great. I mean, there are, you can imagine that H could take a sine wave, diminish it, and also shift it, right? It could do something like that. That's not covered when you just look at the magnitude of the diminishment. Okay, so let's look at a real world example. This is from a CT scanner, and this is a phantom that we had constructed here in the machine shop at UCSD, a very good machine shop, actually, it turns out. And what we did was we took, it's basically perspex or plastic, and we asked the machinist to drill holes at specific separations, 1 diameter separations at different amplitudes in this plastic. And this machinist was able to get these holes down to exceedingly small numbers by essentially sacrificing many, many drill bits because they break when they're really tiny, right? But anyway, they were able to do it. And so we drilled holes in this plastic. And so the plastic itself absorbs X-rays. And so it gives you brightness on a CT scanner, which we'll see. The brightness is proportional to the number of X-rays that get absorbed. Okay, so more X-rays get absorbed, you get a brighter signal on CT. These are holes, and so this is air, and so you get a dark signal, okay? And that signal on a CT scan, air, it turns out, will have a value of -1000. And this has a signal of about 50 or 100 or something like that. So we can look at the contrast between this air hole and the background plastic. And then we can watch the signal actually disappear as the holes get closer and closer together. We take another acquisition, and this is what it looks like. Okay, and so some of those holes appear. And what have we done differently between this acquisition and this acquisition? This one, we used 380 milliamps of current in our X-ray tube. We turned up the current, so more X-rays came out. Okay. And so on the detector, we had a much higher signal to noise function. With this one, we turned the X-rays down to 96 milliamps. And so the number of X-rays and the signal to noise in the data got lower. And one thing that happens when that occurs is the manufacturer actually starts smoothing the data in order to get reasonable pictures. And when that smoothing occurs, you start losing these details, right? And so we looked at the theoretical way to characterize this spatial resolution, and that was for these parallel patterns where I have dark, bright lines at a certain separation. I have a frequency, and as that frequency goes up, I can see the contrast here between the holes goes down. So this is a physical instantiation of that thing that we looked at theoretically, right? This is called a resolution phantom. And the other way of doing a resolution phantom is, instead of these parallel signals, you just put a tiny little dot in there and you look at the point spread function, right? That's an alternative way. We can measure across that pattern and look physically at the modulation of the pixels as we go across there, right? And we can measure the difference between the height and the trough, and that difference as it changes is going to give us that relative change in the modulation transfer function. And so here is the image with the lower MA, the lower signal to noise, more smoothing, and we see that those modulations basically go away. All right, so we really can't see anything anymore here. So that is a direct visualization of the modulation transfer function on a scanner. Okay? And in CT, they make, this is a phantom we made for particular reasons. In CT, oftentimes you'll see, and we'll see later, parallel line patterns, and they're radially distributed where the parallel lines get closer and closer together. And then you just look at them and see where they disappear. We talked about this on Monday, and just to review, if you can make a very tiny object to put in your scanner, such as a ballpoint pen, the little ball, the little stainless steel ball, stick that in there, make a picture. That picture is the point spread function of the scanner, right? And so you want to make a picture such that you have many, many pixels across here, because you'd like to measure with great detail that point spread function, right? So the resolution is not just the size of the pixel, right? I could put 100 pixels across here, right? Such that each pixel dimension was a few microns. That does not mean the resolution of the scanner is a few microns. That's just the pixel representation of the signal that we've got. And this is the spatial resolution of the system. And it's just that point spread function, right? When you're measuring that point spread function, you do actually want to reconstruct the thing with a lot of pixels so that you can get a nice shape. So it's often confused, like the pixel array dimension is often conflated with spatial resolution, and you think, oh, my resolution is, a certain dimension in pixels, but that's actually not the case, right? Those pixels are representing the object, and then a lot of things can smooth the object past that. There's a definition in Princeton Links about local contrast. We'll save this name for this definition, this local contrast, as opposed to something we're going to look at later, which is contrast to noise ratio. Local contrast is an interesting concept because it gives the relative contrast between a target and the background. And so it's defined like this: what is the signal on my target? What is the signal on my background? And I normalize that to the signal in the background. Okay, so it's fractional change in signal of that target versus the background. This turns out to be a sensible way of defining contrast in X-rays, because regardless of what these values are, if we put more and more photons into the system such that we have a better and better realization of these numbers, they change their values, signal to noise changes, but this stays constant. Okay, it's the relative amount of absorption of X-rays. So that's called local contrast. People don't really measure local contrast with their eye-brain system, right? It's difficult. If you ask somebody, what's the percentage contrast between, this and the background, then it's a hard thing. People don't measure that with their brain. It's sort of like the difference between linear, your own gestalt for how big something is. If I say, how big is this room? You immediately start thinking about the linear dimensions of the boundaries of the room. You don't think about the area, unless you're a real estate agent. They think in areas, but people usually think in, not that real estate agents aren't people, but people usually think in linear dimensions, right? Because you quickly know, oh, that's 10 yards. I know what that is. Similar to that, people think in sort of contrast to noise, and that is, what is the absolute signal of this dot what is the absolute signal of the background? What is the noise on that signal? And therefore the signal difference to noise, or the contrast to noise, is what you can wrap your head around really easily. And to measure something like that, you need to be able to characterize the noise in the background, right? So we'll get back to this after talking about noise a little bit. So anybody can see that, the signal here versus the noise, the signal is quite high versus the level of the noise. When we get over here, it seems like the signal is about almost the same level as the noise, right? Because this random signal back here, right, has an amplitude that is almost the same size as the signal. So just, gestalting that, you say this signal to noise is high, this signal to noise is low, right? So where does noise come from? In MRI, the noise is actually quite well behaved most of the time. But most of the time, the noise is from thermal sources. So the coil itself that you measure the signal with has natural noise in it. So if you just had it in a vacuum, you would still, measure noise just from the thermal agitations of the electrons and the resistors and stuff. So there's a noise level there. When you take that coil and you put it up to a patient, you don't do any MR signal stuff. You just put the coil up to the patient, the noise jumps up because you're measuring the thermal, motions of charged particles in the patient. And so the noise jumps up. And so that's a natural source of noise. And it turns out that noise, it's called white noise. And that means if I go along, in this case, in space, after I've made my image, or in time, when I have my original signal, from one point to the next, there's no correlation in the two values, right? Which is a hard thing to imagine, right? So I'm trundling along with my signal. I have a certain value, and then the next point has absolutely no correlation to what that previous value was. That means that's white noise, that it's coming in at all frequencies. We'll see in CT, when you look at the background of a CT scan, that is not the case, right? The noise has sort of a wavy, weird pattern. But in MR, the noise is this hash. It's like a clean fuzz on top of the picture. You guys don't really have a lot of experience with white noise anymore because you've grown up just watching digital signals. And so when things go bad, you don't get white noise. You get pieces of the screen start devolving and things like that. But if you've ever been in your car and you're trying to hook your phone up to the radio and things go awry, sometimes you wind up on an AM radio station in a foreign town, and it's just on some random, megahertz signal, and the stuff coming over the speaker, then that's white noise. It's like, right? And that's the white noise, right? As a kid, our TV had a bunch of white noise superimposed on the pictures, right? Because we were measuring signal from radio waves in space. And it turns out about, I don't know if you know this, but about it's 5 or 15% of that white noise on the TV signal when I was a kid is the cosmic background radiation at 2.7 Kelvin, right? Of the radio waves, right? So when you hold it up, the temperature, the residual temperature of the universe now is 2.7 Kelvin, right? So when you look back at radio signals and you look over the whole sky, it doesn't change that much. It's like 1 part in 10,000. It's all that temperature, right? That's just this radio signal. And so when we were kids and we were watching the Flintstones and things were going bad, we were actually watching the cosmic, background radiation. That's kind of cool. So other things that can screw things up are clutter, which means the image is just really complicated. The signals are complicated, and so you can lose details in the clutter for lack of ability to extract it. And this is why they Google has 900 million pictures of traffic lights, I'm assuming by this point, right? Because every time I want something, I have to identify 3 traffic lights, right? So there's also artifact, and this is not random noise. This is actually a signal that you don't want in the picture. It isn't the object, but it's something about your imaging system has made that signal, right? And so it could be a ghost image. It could be an intensity variation that isn't there in the object. All of these things are artifacts, right? If you've looked at the James Webb pictures that are coming back, you know, when they have these foreground stars that are super bright, right? You see the artifactual signal from the diffraction on these or hexagonal arrays, right? So when you have a bright star, it has these crazy Christmas light. It looks like something on a Christmas tree. So that's an artifact. I don't know why they can get rid of that. Does anybody know? You think they just like it because it looks like Christmas tree? You know, I'm looking at it going, can't they like fuck that thing out? You know, like do some deep learning and get rid of that artifact. But anyway, it does look cool. It looks festive, you know. So anyway, what we can do to combat signal to noise is we can sacrifice resolution. And so here, you know, we have that same increasing noise and a reduction in signal to noise. But as we go down in rows here, what we've done is we've taken this image and we blur it in each one of these boxes here. Now, how do you blur an image? One way of blurring it is say, let's take each pixel. I'll take every neighboring pixel around that one and itself, and I'll average them all together and then put that value back. That's a trivial way to blur an image and also increase the signal to noise, right? Because now each one is the value of all of those pixels, right? Averaged together. And so you get a blurred picture, but the signal to noise increases. So if you have resolution to sacrifice, you can do that, right? Sometimes you don't. Sometimes you really want to see fine details, so you just average longer. So here's two images at different signal to noise levels. It's stark, you know, what's going on here. There's more random fluctuations in a signal that should be constant. This is a 3D printed left ventricle with contrast in it. So all of this should be exactly the same value, this white signal here. And all of this should be exactly the same value. Over here, you can see it's not exactly the same value. That's the noise. It's a CT scan. So what we can do is we can take an area of pixels. We can measure the mean signal, and this we'll look at CT units. The mean signal here is 673, and the standard deviation around that mean. And so how do the pixels fluctuate around that mean? We can look at it here and in the background, et cetera, to characterize the signal to noise. So let's look, we'll zoom in to the background here, and here's a box of the background of a higher signal to noise image, and this is the lower signal to noise image. And ask ourselves, well, how do we characterize the fluctuations of the signal values in this box that should be constant? All the values in here should be the same. The mean value is 195 inside this box. You can plot a histogram of all of the values seen inside that box. Okay, everybody knows what I mean, right? By a histogram. So here's 195 is in the middle. These are the ones that are lower. These are the ones that are higher. And you measure the width of that Gaussian distribution, if it's Gaussian. And that's the background standard deviation, or the level of noise, the noise level in the picture. You can do this with your, pictures you take with your camera. You say, is my camera still performing well? You just go in and you measure the noise level. And now this one, which is taken with fewer photons, so like higher noise level, we still have 190, close to 195. It now says it's 192 in this instance, but the standard deviation in the background is much higher. It's 8.3. Okay, so that's what the noise level is. It's a simple way to basically measure the noise level. It's like statistics you did in underground physics labs, like what's the root mean squared deviation on this data, this string of numbers. If you look at the spatial, this is jumping ahead to advanced topics, but you look at the spatial correlations of the background signal here, is that white noise? It is not, right? Because if I have signals here, like there's correlations of these signals all across that thing there, and then there's a valley down here. So there's lots of spatial correlations to that signal, right? it's not just random from pixel to pixel, right? And this is a particular thing about CT, is that the noise has this inherent structure. And part of that comes from the reconstruction methods used to make CT images. In MR, unless you get into very advanced parallel imaging and some nonlinear techniques, if you just use the Fourier transform to reconstruct, then normally the images just have very white background noise. Right? So now we can go back to our contrast to noise measurement. And so here's pixels across my object. I draw a line through that object and I can sample it multiple times, right? And this line produces this plot here, such that the background was at 195. That's what we measured right here. And then the center of the minimum here is down at 115. So now I have the signal difference, which is 195 minus 115. So that's here. Divide that by the background standard deviation, or the root mean squared deviation, right, of the background, and that was 3.4. So that signal difference to background noise is minus 23.5. And so that is just the signal to noise of that object in our picture, right? And 23.5 is a big number for signal to noise. There is no doubt that you can see that object, right? With signal to noise of 20, that's a lot of signal to noise. In the lower signal to noise instance of this picture, we know where this is, so we just replicate the position, right? So we know we're sampling the object. And now our signal looks like this. Our dip in the signal goes down to 156. This mean is still up around 192. Divided by 8.3, the signal to noise went down to 4. Okay. And so the question is, can you tell there's an object there? Right? So if you look at that, it helps. You can squint, right? That helps. What does squinting do you think? If you squint your eyes like that, does anyone knows what it does? Why you can see things when you squint? It's a way of averaging the background. Just sort of smooth it over. Another, if you want to resolve things, sometimes if you squint, the aperture gets smaller, and so you can resolve things at a distance better. Those that wear glasses know this. So now the question is like, well, what is the threshold of this number such that I can always detect an object, or detect an object, let's say, with 99% confidence? I'm only going to be wrong once every 100 times, right? So you can just measure that. That's, if this number is about 5, then you're going to do about 1 or 2 in 100, or we'll be wrong, right? And that's called actually the Rose criterion, where for humans, when they're looking at simple patterns like that, the threshold signal to noise to detect the pattern is about 5, like to be super confident that you've got it. As the signal to noise goes down, it depends how much of a betting person you are. You know, you can say, well, I think I'm going. You can look at it and assume that it's giving you information to make the decision, or you can just always say it's there, right? And you're right half the time. So depending on, you know, what the population of actual signal are behind that.
Excuse me.
Yes.
Where's the 3.4 and 8.3 come from?
Oh, sure. Let's go back here. This is the 3.4 was the width of, if I made a histogram of all these pixel values here, I can do 2 things. One is calculate the root mean square deviation about the mean of all of these pixels. And that number is 3.4. And when I plot it, it looks like this. It's narrow. And this one is 8.3.
Oh, just divide by the standard deviation.
Exactly. Yeah, the sigma value that we measured. Yep. So when we go here, there's the 8.3 and the 3.4. So standard deviation. Great. Thanks for the question. Okay. Yeah. This is a very good question. Sometimes if the image is complicated and there isn't a nice smooth place to find the background area, you can't find the background area, right? So how do you then estimate what the noise value is on your image? It's a great question. In this case, we had a nice spot. We could measure the background area. In many cases, it's there. In MR, you can oftentimes just go off into the air beside the patient and measure that. Or, in some place where you get very little signal, like part of the lung or something. But then there's a trick. If you can take two images, right? You take one image and the next image of this exactly the same object. If I subtract those two images, what's left? Just noise, right? And so basically you just get a noise field. And that noise field will have a root mean square deviation that is √2 times higher than the actual root mean square deviation, because you've used two of them, right, in that subtraction. And so that's the trick. But oftentimes you can't do that, right? Because you don't want to take another CT image of the person or whatever. But when you're doing phantoms, it's often a good idea when you're imaging phantoms to image them multiple times. And that way you can always figure out, what the background noise is. Okay, great. Those are good questions too. So we're going to move on to X-ray physics. And this is like, how do you make X-rays? And then how do X-rays get absorbed by humans? And then how do you make a picture of the relative absorption of those X-rays? Okay. Again, if you want to watch this in 2x or whatever, here it is here. So here's a plain film X-ray picture where a patient just put their hand down on a detector, and then the X-rays were projected through the hand, and then this picture came out. And you can see that it's bright in the places where the X-rays were absorbed. Okay, so in the bones absorb X-rays more than soft tissue. So here's soft tissue back here, and here are the bones. They're brighter. And traditionally, this is what X-ray or what radiologists looked at, were these negative images, basically. And because the X-rays would have high fluence out here because they didn't get absorbed by anything, they would hit the film screen system, cause flashes in the fluoroscopy part of it. And then on the film, you would get black because it converted all the silver iodide to this black stuff, right? And so you get a negative. And so oftentimes, so when CT is reconstructed, we still go to the trouble of doing this, of inverting the signal so that we get brightness where there is high X-ray attenuation. And so here, is this the right or the left hand? I leave you with that problem. Okay, you can comment. Okay, so here's the basic X-ray imaging chain. This has been the way it's been for, like, as you saw, 100 years. You have an X-ray light bulb, an X-ray tube, X-ray tube it's called. Let's see here. Sorry. Good. Underneath the patient is a detector. These are all digital detectors now, because the image goes off to a computer, as opposed to a film screen system where you had to pull the whole thing out and send it through a developing process. And that took a lot of labor, a lot of chemicals. Kodak, Fuji had businesses in the tens to hundreds of millions of dollars of these film screen systems. And so obviously they had to pivot if they were going to stay in this business and make all their stuff digital, right? So they had very big research labs to go that way, to go to digital imaging quickly. And then there's our patient. And so an X-ray that is generated in our tube goes either through the patient and hits the detector, or it gets stopped by the patient. Ideally, that's how it works. Okay. And we get a differential absorption, okay, depending on the path through the patient. So here's the electromagnetic spectrum and its wavelengths and the energies of those photons. X-rays are in this area of this spectrum from about 70 to 140 kilo electron volts is where we're at, and here are the wavelengths here. You know, in the news lately is this area here, obviously, right? For the Webb telescope is bringing back these really cool infrared pictures. And as we discussed before, the radio waves, you know, you can pick up with your just your antenna if you want to measure the background radiation. This is a traditional X-ray tube. There are new fangled designs of these tubes to try and get higher powers, but this is the way it was done for, I don't know, 85 years or something. And I'm going to flip that picture over because the diagram was in this orientation, the diagram in the book. So here's our X-ray tube in that same orientation. Sorry, gravity's pulling it to the ceiling. This is a motor here, and the motor spins this axis, and on the axis is a disc, like here. And that disc spins around at a high RPM. And here we have a cathode, which we put a lot of current through, and it heats up a little filament. And what comes off of that filament as you heat it up are electrons, right? They bubble off this filament. And I don't know, who did undergrad physics? Anyone do undergrad physics? Did you, anyone? No? Oh, okay. We had this great experiment as undergrad where you boiled off these electrons, and then they went through a magnet, and you put them through a tube where they essentially caused fluorescence in the tube, and you could change the beam and path and everything of these electrons. This is the way televisions used to work, right? You'd have these electrons going to things. But anyway, so we have a cathode, boils off electrons. You put a high voltage. This is a positive anode, and this is negative cathode. And we have another dial on the X-ray system that is the voltage between the cathode and the anode. I can just click that voltage up, click, 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 click. And then as the voltage goes up, the acceleration of the electron, when it gets boiled off, and it's attracted to the anode because there's a positive field there. And as the voltage goes up, it goes faster, right, towards the target. So this is the target. The electrons are the bullets. And when they hit the target, what happens is X-rays come off the target. Okay, and that's how you produce the X-rays. Here's a diagram of that system. Again, the motor, and we're going to put a high voltage on the anode here. So there's a voltage coming in the back. This is in a vacuum so that the electrons, have a free path to the anode. The reason this spins is because if we just hit one target, or the target did not spin, it would heat up extremely quickly. And so you spin it so that you get a much larger area over which the electrons are hitting, and you have time to cool it. And the cooling is done conductively. It just goes out here. The filament itself is tungsten, excuse me. And that's here. This target can be a number of metals. It can be tungsten or molybdenum for mammography to get a different energy spectrum. And what else do we need to know about this? And then the MA, our dial for just increasing the number of X-ray photons, is equivalent to increasing the number of electrons that are going across here. This is angled here so that basically you want the X-rays to shoot out of the tube this way, right? So you put an angle here, and then normally the target itself is a rectangle. It's not a point, because if you focus all of these electrons down to a point, you would burn out that point very quickly on your tube. And so it's usually a very small rectangle is the target. Yeah.
The idea here is that because of the voltage on the anode, electrons being attracted from the cathode.
Exactly. And if we double the voltage, the energy at which that electron hits the target is essentially doubled. Right. Exactly. Yeah. And the energy of the X-rays is given in kilo electron volts, is the unit of energy of the X-ray. So I can have a 70 keV X-ray come out, or I can have 140 keV X-ray come out. That's kilo electron volts. It's because there's, you know, basically that's how many volts is across here when the electron hits it, right? That energy is released with the photon. So in X-ray production, a couple of things can happen. So the electron in our beam there, hitting the tungsten target, goes through, it bumps into another electron in an atom in the target, and that shoots off what's called a delta ray, which is another electron, which is just shot out of that target thing. And it can deflect and then do that again and do that again. And so it's just knocking electrons all over the place. And all that does is create heat, right? Because all of these electrons, you know, you thermally are agitating the system, right, by doing this. However, the way that X-rays get generated is the electron comes in and hits a particular electron here, ejects it, okay? And then an electron from a lower energy orbital, I'm sorry, a higher energy orbital, say a p orbital, drops down into the vacancy in your atom that was produced by ejecting that electron. So those inner orbitals basically get filled first, right? And so when something comes out, an electron from a lower energy orbital or a higher energy orbital will drop down into that slot. And when that occurs, that emits a characteristic X-ray. Okay, the energy difference there gets emitted as a photon, as an X-ray. That's the primary, one of the primary generations of characteristic X-rays, or the generation of characteristic X-rays that we'll see in the spectrum in a minute. But principally, most of the X-rays coming out of your target are produced by this process, and it's called Bremsstrahlung radiation, and Bremsstrahlung is German for breaking. And the electron goes from the cathode, and then when it gets into the anode, it gets deflected in its path by an interaction with a nucleus. It doesn't hit the nucleus and cause some kind of nuclear event or, you know, transformation of a proton to a neutron or anything. It just gets accelerated. When it gets accelerated, it essentially emits a photon. Okay, so it remains an electron traveling through the object. It has lower momentum, right? And it's changed its direction of momentum, and a photon has been emitted. Okay. This is the primary source of X-rays coming from our target, right? And when you look at what is the energy spectrum that comes out of that target, like how do we characterize all the X-rays coming out of there? They come out at different energies depending on the, you know, nature of this interaction. So this can really bend hard this way, and then a higher energy electron comes out, or a photon comes out. If we plot the relative number of X-rays that are coming out of the target as a function of energy, the plots look something like this. And let's say we've adjusted our voltage between the anode and the cathode to 120 kilovolts, right? And the highest X-ray we can get out of that thing is an electron that transfers all of its energy in the collision, in that Bremsstrahlung collision, out as a photon, and it's coming out at 120 keV, right? Not many of those come out, but it can happen. What happens is that as those collisions, as you look at more and more of those collisions and the probability of those collisions, it goes up linearly as the energy goes down, right? And so the density, or the amount of 80 keV photons you get, is the relative amount is this, and then the number of 40 keV photons is this, right? And this curve would continue in this form all the way to zero. It would just go linearly up to zero. However, what happens is that the lower energy photons that are produced inside the target get absorbed before they get out of your X-ray tube, right? So they get absorbed by the target itself. So the X-ray is produced in, at some depth inside the target. The X-ray starts moving and it gets absorbed by the target itself, or it can get absorbed by the glass, or it can be absorbed by a thin piece of copper that we put at the output of the X-ray tube. The reason we put that there is we really don't want these X-rays, right? We don't want to shine these X-rays onto a person because none of them will get through the person. They would just get absorbed by the person. Yeah.
More energy photons that get absorbed, that's velocity dependent, or is it just on energy?
It's mostly say we had our X-ray voltage turned up to 120. Okay. There'll be a distribution of energies of those electrons, but the peak one is 120, and there's be some kind of energy distribution of the electrons. But principally, the way this relative amount of energy is generated is the probability of this, right? So the probability of a slight bend and a 20 keV photon coming out is much higher than a collision that is direct back and a 120 comes out. So it's the relative probability of each type of Bremsstrahlung that gives you this relationship here, okay? And if we turn down the voltage to 100, exactly the same process, it just starts at a smaller energy. I can't have something over here because I just didn't turn my voltage up high enough, okay? So the relative amounts of those X-rays look like this. Remember when we looked at this characteristic line here where we ejected the inner shell electron, and this characteristic line would come out, they look like this, right? So there's a peak in those photons because of that process. So you get these little peaks in the, it doesn't have much bearing on how we use this to make an image, right? We'll see though, it can have a bearing on contrast in the other direction, how photons are absorbed. So just to review, we don't want low energy X-ray photons because they have essentially zero probability of making it through the patient. So they'll just get absorbed by the patient. So we don't want to just send radiation in and not have an image on the back end. So filter them out first. And then all of these X-rays are very good for making a picture. And you can ask yourself a really simple question like, what ratio of X-rays that enter the patient should come out at the back of the patient to make a good picture? 1% should come out, 2%, 50%, 90%. It's an interesting question, right? Okay. So now on the other end, now we have a photon. A lot of these pictures look similar to the generation of photons with electrons hitting the target. This now, we have the photon, forget about the electron, we have the photon, and it's going to enter the person and it's going to interact with matter. A lot of these diagrams look the same, but remember, the thing coming in from the left here is a photon, all right? Yes?
For your last point, what is the trade-off between how many photons or X-rays are passing to the patient versus, is it like how good a picture, how good like you get, or like for example, 90% of them come out?
Yeah.
Is it going to be a really good photo or?
Well, it's what really matters is the relative amounts of photons that come out for the structures you're trying to image, right? You want to generate the highest signal difference between those two structures that you can, right? So if 99% of the photons came out, you would get a very flat contrast picture, right? Because you'd have all these photons everywhere. And quite interestingly, when you go to higher and higher energies, the contrast starts getting pretty flat. If only 1% of the photons come out, you start running out of photons to make a picture, literally run out of photons. And this actually happens in CT. There are certain angles where you're going through a lot of tissue, like through the right arm, then the chest, then the heart, then the spine, then the rib, then the left arm. You're going all the way through, and you'll get down to literally 1, 2, 10 photons on your detector at that angle. So there's a dynamic range. My guess is 50% is a pretty good number. I don't know. You can work it out. So here now we've got photons coming in. These could be anywhere from, 40 keV all the way up to 120, depending. And there's two major effects. One is the photoelectric effect, and one is Compton scattering. Okay. In the photoelectric effect, the photon essentially gets absorbed by the atoms. So this is like a chemical thing, right? So we're talking about the photon interacting with the electron cloud of an atom, and it hits one of the electrons and knocks it out, right? And in just the way we saw with the electron collision, one of the outer electrons drops into that slot and you get characteristic radiation coming out, right, as a secondary photon. And this can be quite different in energy than your original photon that you put in. And another way is instead of just characteristic radiation coming out, you can have a two-step process where one electron fills in the hole, which basically makes a hole in another level, which one of the outer levels fills in, and the energy difference there is close enough to basically the ionization energy of that atom that it just boots out an electron instead of a photon. That's called an Auger electron. The details of this aren't that important. What is important is that at this photoelectric effect, what's going on is the incident photon is essentially getting completely absorbed by the atoms in the object. Okay. Then we have another mechanism called Compton scattering. And what happens here is the photon gets close enough to the electron to knock it out at some momentum, right? And the original photon itself is diverted at some angle theta. It's scattered at some angle theta. And the Compton electron goes into the person and just goes brrr and loses its energy inside the person, right? And it can cause some problems as it's doing that, right? And then this photon that got scattered, ideally, this angle is high enough such that this photon just misses your target, because you really want to just absorb, you want to see where this absorption occurred. You don't want to create a new photon, right, at a different angle. That'll just confuse things. That's called scatter. So ideally, this angle is high enough that you miss the target, or you put a grid on your target such that photons coming at high enough angles get absorbed in this anti-scatter grid. Okay. And so this is called Compton scattering. So these are the two major ways that the patient absorbs the photons, right, that you've made in your X-ray tube. So the probability of the photoelectric effect, when you do the physics and write it all down, it goes to the 4th power of the atomic number of the atom, right, divided by the energy cubed, right, of the photon. So that means this is the energy of our X-ray photon. As the energy gets smaller, the probability of this event goes up pretty quickly, right? Because this is 1 over cube power, right? And then for Compton scattering, it goes linearly with the atomic number. So it's just basically the number, the electron cloud around the atom, so the number of electrons there. And as we'll see, over the energy levels that we use, Compton scattering is basically constant. Like it doesn't change a lot with energy over the energies that we're going to see. Most of our imaging is done up here between 80 and 120 keV. And you can see the percentage of interactions with matter, say with water or humans, or this is in water, that you have Compton interactions up at these energies is, 97, 98%. So mostly what's going on is this Compton scattering in our pictures. And then as you go to lower energies, you get basically lower and lower amounts of Compton scattering and more photoelectric effect. Okay. So down here, we're basically sending low energy photons in, they get high probability of photoelectric effect and pushing electrons out onto trajectories through the patient, which is a bad thing because it's that kind of energy that can lead to double strand breaks in DNA and things like that. So you don't want that event occurring, if you can. So here is, all these references are down here if you want to look it up in more detail. But this curve gives the the relative amount of X-ray attenuation. Let's call it that. That's called the mass attenuation coefficient. Relative amount of X-ray attenuation as a function of energy, where this is keV. And this is 200 keV right here. So we're working down in here, right? So here's photoelectric. And here, that's the relative amount of attenuation. And this is Compton. So you can see over our range, Compton is basically constant, right? It's not going to change that much over energy. So this is what we're interested in terms of our imaging experiment. You can see, though, that this gives us an opportunity with X-ray imaging in that if I take 120 keV image, which is right about here, the amount of photoelectric effect versus Compton absorption is a certain ratio. And if I took another image at, say, 50 keV, then I have a much different ratio between photoelectric and Compton, right? And so that gives you the opportunity to take two pictures that will have different contrast, right? Because the chemical interaction of the X-ray, the photoelectric, and the Compton are quite different in those two pictures, right? So that's called multi-energy or sometimes dual energy X-ray imaging. It was invented a long time ago. It's been done for many years. It has never really produced a application that just blew everyone away, right? That changed the face of diagnostic medicine. It sure looks like it should, but it hasn't yet. So let's just review how this is going to go. We have an X-ray tube, set the KVP, set the current for the amount of X-rays that we're going to have. We have a filter here to get rid of the X-rays that are below a certain energy that we don't want to put in the patient. We have a trajectory of that X-ray through the patient and then some kind of detector back here. This is a really old picture because this detector is a film screen system. And that means what used to happen with this, you had an anti-scatter grid. So if you had something at a really high angle, it would get stopped. So if I have a Compton interaction and my photon comes here and then comes off at this angle, boink, it gets stopped by this thing instead of giving a signal right here, right? And then down here, we have this grid that essentially when an X-ray enters the film screen system, it gives a flash of light, and then the film is exposed with that light. That was the old way. Now, most of the time that X-rays are detected either digitally with materials that flash when X-rays hit them, and then you have a photodiode that counts up the sort of amplitude of the flash, or increasingly we're just directly detecting X-rays with X-ray counters. And then you can figure out what the energy of the X-ray is when you detect it, which is pretty cool. You would think with CERN and all these places, like they have to detect tons of different energies of particles and stuff very quickly, right? So we should be able to do it on this little experiment, right? So here's a few definitions from the book. In terms of the intensity of the signal that we're going to measure at our detector, it will be proportional to the energy of the photon that hits the detector. right? Because it's packing more of a punch if it's got a lot of energy, and the fluence. And the fluence has a very sensible definition of the number of photons per unit area in a unit time. Okay, so that's just sort of number of photons that are hitting it. Now, if we want to truly compute the fluence with great accuracy, we need to take into account the fact that the relative number of photons at different energies has a function that looks like this. It's called a polyenergetic X-ray spectrum. And different X-ray tubes have different functions here, right? And so when you are using a CT scanner, and if you want to simulate in great detail what's happening with your scanner, normally what you have to do is first convince the manufacturer to give you these graphs or some reasonable facsimile of these graphs as to, for your X-ray tube, what does the energy spectrum look like for your X-ray tube? And then the fluence itself, right, is the integral under this thing S of E. This is E here, and this relative number is S of E. So we just integrate under the whole thing to get the total fluence, right? And then the intensity is that integral of that point by point fluence times the energy at that. Right? So let's look at the attenuation of X-rays and how we're going to model that as they pass through the material or a patient. It's a trivially simple model. It's first order differential equation, just like you have a cold glass of lemonade and you look at its temperature over time. All of those things you did in your first differential equations class, right? If we have 1,000 photons and then we have this material, we have, say, some thickness of this material, maybe it's water, and then what comes out of the back is 800 photons because 20% of them got absorbed, okay? And then when it hits a replicant of this target here, 20% of these photons get absorbed, so we get this much out of the back. Same deal, replicate it again, 20% get absorbed here, and we get this much. If you plot that, it looks like this, right? And the function is a simple mono-exponential, where x is the amount of distance traveled through the material, or the thickness of the material, and mu is the characterization of that material's ability to absorb X-rays, right? So it's a empirical parameter that just says, look, I have a mu value for water and a mu value for steel and a mu value for concrete stuff, and say, how does it absorb X-rays as a function of distance, right? And so this is the fundamental quantity that we're going to be interested in that when we take a CT image, effectively what our CT image will be is a map of the mu value at each pixel. That's what the CT image will be, okay? So we look through and I say, oh, here's bone. It will have a value that is linearly proportional to this mu value for bone. Blood will have the mu value of blood, and air will have the mu value of air, etc. So that's what our picture is going to be, right? Is this thing. It's called the linear attenuation coefficient. And oh, this is from the book. Jerry derives this same equation in the book. We won't pause for it here. We're running out of time. But I do want to introduce this, which is the half value layer. And again, when you ask what do people think about, they don't think in mu values usually, because it's sort of number of E drops per unit mu value or whatever. So a half value layer is a simple way of getting a gestalt of how many X-rays get absorbed in your sample, right? And so the question is, well, at what depth of my sample, let's say it's water, at what depth are 50% of the photons absorbed where they gone? And so that's a very simple equation, right? So it's that if I have this many going into my object and this many measured, and I set that to a half, it's mu, and that's the half value layer. And then it's in centimeters. And so you can think about it in centimeters, yeah.
There a significance with this half value, like 50% is like the target that we're trying to reach?
Well, it's sort of a 50% you can think of really easily, because if you have, say that if you know the half value layer of water, and say it's like 10 centimeters or something, then you go, what happens at 30 centimeters? So it's just a half times a half times a half, right?
Oh.
So it's pretty easy to do quick calculations in your head. It doesn't have to be a half value layer. It could be in 1/E value layer, but then you'd be back to
That's more of a-
right. Right, exactly. So it's just a handy thing to have in your pocket. And the engineers that I work with, at the companies and stuff, they know the half value layer from many, many materials. And then they look at a picture, and when they look at that picture, they know how many photons got from here to there. Right? Just like that. Right. So that's how you can think, because you go, oh, I've got this many centimeters of blood, I got this bone. What's the half value layer? And just add it up, and you can do it like that. Right. So half value layers and mu, okay, so remember half value layer and mu is the same thing, are energy dependent in that to stop higher energy X-rays, you need more stuff. Okay, that's the thing to remember. If I got a high energy X-ray, I need to put more stuff to stop it, right? So at 30 keV, I only need 2 centimeters of muscle, so that much muscle to stop half of the 30 keV photons. But 150 keV, I need 4.5 centimeters, so double that, right? Right. So these are nice round numbers, right? That we're working with here, right? So that's another reason why half value is probably a good thing. Bone, you can see it's about a factor of 2 there. Right, 13. Oh, this is an example of why this definition of contrast, where you have the signal at A minus the signal of B divided by the signal of A, when you define contrast that way and you write down the expression for the amount of attenuation along this path at A and the amount of attenuation along this path at B, and you write down this and you solve it, it comes out to a very simple expression, right? This is like a perturbation, on the contrast being 1 is just this exponential mu times whatever that delta is, and that gives you like 0.98 or something like that for the contrast. So that's just a definition. Now let's look at the attenuation of X-rays when we're doing imaging. When we're doing CT imaging, the X-rays usually are emitted from a point that's up here, and so they come through the patient on paths that diverge from that point, and they get, and our detector is wrapped around the patient down here. So if we look along this direction, we say, okay, we have attenuation that is occurring along the pathway of our electron or of our photons, and our detector is down here, and it's going to measure what's coming out of the patient. But I'm going to go through things that are not the same, right? First I go through muscle in the muscle wall here, and then maybe a rib here, and then essentially air through lung tissue, and then some blood, and then air. So mu is changing as I'm moving through as my beam is moving through the patient, right? So this is the expression for the change in number of photons, right? Given a starting with n as a function of mu. But now mu is a function of x. Let's just draw x along this pathway here. So the way we calculate the number of photons that are still in the beam as a function of depth, or x in here, is this equation. So it's the number that started here that hit the surface, right? And then we integrate from 0 to X if I want to calculate how many are here, or X if I want to calculate how many are down here. And you just integrate the mu values as you move through the sample, right? So the mu value of muscle is relatively low, and then bone and a rib is relatively high. And so that mu function changes. And you just integrate across that. And that's the net effect of traveling through along that line through the patient. If you'd want to do it absolutely explicitly, you also have to include energy. And that is the easy way to think about this is I'm going to break this problem up into 100 problems. And I'll have 100 different energy bins. And I'll make a picture at every energy bin, and then I'll add all those up. And that's the equivalence of this integral here, where we have this function gives us the relative amounts of photons at that energy. And this gives us our intensity when we do the integral, including the energy. That's a real pain in the neck. And oftentimes, most of the time, this is not done. Right? Most of the time, you estimate your beam with the average energy of the whole beam. Okay? And it works out most of the time, unless there's certain times when it doesn't work out, like you have metal in the field of view and it changes the energy remarkably and stuff like that. So here are some mass attenuation coefficients at 20 keV, and this is more 100 keV. 100 keV is where we do CT imaging or diagnostic imaging. So air, water, bone, muscle, etc. And these are the relative values in centimeters squared per gram. They're normalized to mass because bone would be ridiculously high because it's so dense, right? So you just normalize it to mass. And then you can get these off the NIST website or anything, all of these values. Okay. But you can see why half value layer is easier to remember because you're not going to remember these numbers, right? So, and here's the relative linear attenuation coefficient values as a function of energy. So this is linear attenuation coefficient on a log scale. This is energy on a log scale. Bone, we get less attenuation as the energy goes up. Same with muscle and soft tissue. So getting the most relative contrast from, say, fat versus fat and muscle, you'd probably want to work over here instead of over here. However, this is only at 17 keV, so none of the photons are going to make it through the patient, so you can't work over there. You have to work up here at about above 70 usually. It's somewhere between here is where we work with these things. And then there's a phenomenon called the K edge. And as the energy of the photons gets larger, what can happen is in this contrast agent, which has iodine in it, there comes a point at which you cross an energy threshold that you can now eject the K edge, the K level electron, the K shell electron. And so it's like a binary thing. On this side of the energy, you can't do that. You don't have enough energy. On this side, you can. So you get a big boost in absorption because all of a sudden you have a cross section for hitting these K things. That's called a K edge. And that's used in imaging in trying to position certain energy levels in a picture to pick up this K edge with a contrast agent. And one of those K edge contrast agents is barium, which was, remember this guy? It was in his milkshake, right? And so you get this really high contrast with low energy photons. And another source of high contrast is iodinated contrast agent that you inject in, and we saw this the other day. You can do it also in the brain. You can inject up into a carotid to look for something like this, which is an aneurysm, and luckily the imaging system produces a big red arrow. It says, there's an aneurysm, so it's really convenient. Okay, we'll leave bean hardening till next time. And so I guess we'll see you on Monday next week, and I'll stick around for any questions.
Thank you.
Sure, any questions from you guys online there?
You have a quick question.
Yeah,
Logistics wise, is there any plan to open more seats for the course? I think there's a few people, myself included, on the wait list.
oh, is that right? Okay, we can look into that today. I'll talk to Tom about that. And I think it's probably feasible because you know, you can take it online. The only issue we're having right now is trying to figure out how to do the projects with so many people, but we'll
Right.
get through that, you know, and we'll try and we'll ask how long the wait list is and see how realistic that is.
Cool. Awesome.
Great.
Thank you.
Yep.